All right, today I would like to introduce you to Richard Olenick. He is from Illinois. He got his bachelor's degree up there at the Illinois Institute of Technology.
Right.
And then he did a PhD at Purdue, which is the alma mater of Dr. Hathaway. So these guys go way back. And
Way
he's
back.
Gonna, yeah, way back. And he's going to talk to us about dwarf novae and understanding type 1a supernovae progenitors. Now, if you're interested in this stuff, and it's really exciting, I would encourage you to join us for a lunch after the seminar where you can ask all your cool questions about astronomy and other things. But until then, let's give our speaker a warm
Thank you very much. How many of you are in engineering? How many of you are in astronomy right now? Anybody? Is anybody taking astronomy? You're all interested in astronomy, right? Good. That's good. How many of you have done any computer programming? Okay, good. What language do you know? Java, C++. Okay. Python? Good. Okay, so we're going to have kind of a combination of all those things. And I'm going to be talking about my work with undergraduates. So first of all, down here are some undergraduates that we worked with in the last few years who've already graduated from the university. And I have one more this current semester that will be finishing his thesis. So at our university, for a bachelor's degree, you have to do research and write a 35-page thesis. And so this is their research for it. So if you do an internship with the Department of Energy, you would have sort of a similar background that we use. Also, you'll be hearing a bit about Russia, because I work with a Russian colleague in Moscow, and I have another colleague down in Florida. And so we've kind of made this team in trying to tackle a problem on dwarf novae. So let's start with a few things of an outline. I'm going to try to describe what cataclysmic variables are. Probably never ever heard of these things. And they're, I think, quite exciting. And then we're going to see what powers them. And then we're going to go into actually how we take measurements of them and figure out what's going on and how we believe these are what lead to a type 1a supernova. So let's start with a quiz. So what's hotter than the sun and about the same size as the Earth? Dwarf star, white dwarf star. Okay. And white dwarf stars, are they just like that, or does anything happen to them before? Were they always white dwarf stars? They became red giants, so they're like a normal star that could have swelled up and then shrank down. Yeah. Okay, good. Do you know a familiar binary star? Anybody know any binary stars that you've seen through a telescope? How about Alberio? Have you ever heard of Alberio in Cygnus? Sometimes called the Notre Dame star. It's blue and white. Blue and gold, rather. Blue and gold. Our colors are blue and white at my university. So I've got a binary here. They orbit a common center of mass. This one has equal mass stars shown over here. But what do you think happens to how long it takes them to orbit if the stars are really close? Time decreases, a lot less time. Okay, so it takes us 1 year to go around the sun. The binaries we're going to be talking about are taking about 2 hours to go around each other. 2 hours. Those are stars going around each other with a period of 2 hours. And I'm going to mention very briefly the hottest interest right now are ones that are going around about 35 minutes around each other. Just unbelievable how fast these things are moving around. So there's a lot of interesting physical effects that come here. So first, the definition. A cataclysmic variable is going to be something we're going to call a close binary. And it's made particularly of a white dwarf, which is usually the heavier star, and the secondary star that is usually a red dwarf. So it could be a star a little cooler than the sun, a little smaller than the sun. And it turns out there's maybe about 360 of these that we know about. So there's not lots of them, but we know a bunch of them, and we keep discovering more as we get better technology. As we're going to see, the interesting thing about them is that one star feeds off the other star, that they actually exchange mass. And that's what's going to lead to all this interesting behavior with it. So, let's take a little look at binary stars. Everybody knows Star Wars? Tatooine had a binary star. Did you ever notice, though, in the movie, I don't see it here, I think there's one other point, he had two shadows from the two stars, like for good and evil that he has, you know. Good symbolism. Okay, so here's a normal star, binary star up there. That's what we call a detached. They're, say like Albireo that I showed you, might have an orbital period of a few years to go around. If the stars are closer, we can call them a semi-detached, where this star is actually filling up something we're going to get into, and the other one is pretty close to it. And then it may even be in the evolution that they get so close, as in the case of those 35-minute orbiting stars, that there's really only stuff inside and there's all this gas around it. We call that a common envelope that's surrounding them. So, just one quick little thing here is that we start off with normal stars. As someone mentioned earlier, one becomes a red giant. And then when it does that, if they're close, it could actually envelop the other star at that point because it swells up. So our sun will probably become a red giant and swell up and up to our orbit, for example. So these that start off pretty close, they could be kind of inside. And then as the other star becomes a white dwarf, it shrinks down from the red giant stage. We get to see two separate stars again. So we're kind of over here. And then we're trying to figure out what happens along here. So this story is not really totally known yet. And I'm going to give you part of one of them, branches, and how we can approach things. So, we start off, we have a binary system that's pretty close. We have periods on the order of an hour to maybe a few days. And then there's different structures. And one of the things I hated, my PhD's not in astronomy, it's actually in high energy theoretical physics, but I always liked astronomy and astrophysics, so I learned all this other stuff. But I hated it at first because you name classifications of stars by the first star that you find. I always tell my students astronomers are curmudgeons, and whenever they make a system, they'll never change it, no matter what. So even if you have to really do a lot of weird things to keep that system, we do it. So we name these by usually the type of star that's first discovered. Two branches. One is if the white dwarf has a magnetic field. Does our sun have a magnetic field? Yeah. Okay. Does Earth has a magnetic field? The sun has a magnetic field. So we think stars probably all have magnetic fields. And what do you think happens if a star shrinks down to that white dwarf stage? What happens to the magnetic field? It would increase, become pretty strong. So we have these have really strong magnetic fields. We don't see very many of these, and they don't follow what we're going to be talking about. Intermediate kind of do. The magnetic field is not as strong, maybe on the order of a million Gauss. The sun's is about 1 Gauss, so a million times stronger. We're going to be over here in these dwarf novae stage. And that's going to be very small, almost negligible magnetic fields. And then there's going to be different types depending on how we observe them. I'll go into it. So the main idea is that we're looking at a binary star system and see what happens. Well, there are also things called novae and supernovae. And a supernovae isn't just a big nova. It's going to be something else. But they're all tied together, oddly enough, which originally we didn't know that. So here's a star that before and once it became a nova. Nova is just a star that brightens quite a bit. There was one 2 years ago in the summer that you could see with your naked eye. Unfortunately, you'd have to know beforehand, which you wouldn't have seen it, and then it was there. So most people kind of didn't notice it, but I was in Michigan and I went out and found it and could see it because it wasn't on the map as being visible originally. So, these are stars that seem to brighten occasionally for a while, and then they could do it again some years later. So they kind of can do this over and over again. It's the idea with a nova. All right. Well, one of the things recently with advancing technology, this is an artist's conception, is that when a star becomes a nova, that's what's happening over here, it creates a lot of gamma rays, and we actually can observe those gamma rays on Earth. They're called gamma ray bursts. And there's all sorts of gamma ray bursts, but this is one type of thing. So that's been an interesting thing. So a question that comes to mind is, why are these stars doing it? Why can they suddenly become much brighter and then we don't see them anymore? So the key is going to lie that novae, dwarf novae, and supernovae are all connected to these binary star systems. So here's another artist's conception of what we're going to be looking at in more detail. Here's our red dwarf star. Remember, a white dwarf is about the size of the Earth. So to give you a perspective, from here to here is about the distance from the center of the sun to the surface of the sun. Okay? So they're really close. If you were to put these inside the sun, this at the center, this would be right at the surface of the sun. So they're very close stars orbiting fairly rapidly. But a lot of things happen when they get that close. Let's skip the polars and go on to here. We said the periods are close. Well, one of the other interesting things we find is that if we look at these binaries that are close, the orbital periods seem to peak around here between 3 and 4 hours. There's a real big peak between 1 and 2, and there's hardly any between 2 and 3 hours. I mean, there's a gap. We want to know, why is there a gap there? And then again, there's very few somewhere over here, 1 hour, and these are the other one I mentioned, around 40 minutes. There's some of those, and this is the number. There's about 10 of those. Actually, there's more. We're currently writing a proposal to have the Kepler satellite take some data for us, and so we have to find candidates in the field of view for different times and submit those as targets that they will then be getting the images of and send us the data in a few months. So there's about 10 of those. Here you can see there's maybe about 80 or so in that range. Here there's maybe about 40 in that range. But there's this, we call this the period gap here. And we think that the stars are going to maybe get closer, faster, move here. And we're trying to understand what happens to these, because do they go this way or do they go that way? If they are close and they start getting closer and their orbits becoming smaller, their period shorter. So, let's go. Now, a little bit of math. If you're in engineering, you'll like this. Everyone knows where center of mass is, right? Okay. So here's the center of mass. Here's our 2 stars. This is the white dwarf. This is the other dwarf. Does everyone agree that if you had the Earth and the Sun, there's a point between the Earth and the Sun where they pull each other something equally? Force would cancel? Okay. That's the same thing here that we're going to look at, except this is rotating. And it's rotating really fast. So that calculation is a little bit more involved, but we are able to figure analytically, not analytically, but computationally figure out things like it. So here is that point. And since it's rotating, this whole thing's rotating around, pointing with it. It's not at the center of mass, because they're not just sitting there. It's going to be somewhere else. Center of mass is probably over here, a little closer to this star. So it's somewhere over here. But what this means is if matter is in here, it all would want to fall that way. If matter is over here, it'll all fall towards this star. And the interesting thing will be that any matter coming from this star can actually go through this point and fall in the other star. And that's how it feeds that star. And this is called a Lagrange point. And this shape, I'm going to show you a 3D one, is called a Roche lobe. Has nothing to do with insects that infest apartments, but Roche, R-O-C-H-E. And so here are two stars again. This would be the white dwarf. This is the other star. And this is the point where if this star were to become swell up towards a red giant, start to fill its Roche lobe, matter can then flow through here, wind around, and eventually settle on this star over here, which means it starts gaining mass from it. There are other Lagrange points in here. This is one where matter could escape from this star. This is one where matter could escape from that star. And these are kind of some other stable positions. So, yeah, this is good. Everyone knows potential energy? Okay, so here's a curve of kind of the potential energy. And you can see it's got two valleys in it. So there's a hump in between, and if matter can go from the one hump, which is going to be over here, that other one, over that little hump, from the well over that hump that's going across here in the contour map, then we have the red dwarf feeding mass to that white dwarf star. And one other look at this. This is the same kind of contour map of our two stars, and these are going to represent constant equipotentials for gravity on it. But the more interesting one is here. Let's see, right here. So again, if we go to the binaries very far apart, nothing happens. Here's semi-detached. Notice this Lagrange point is right at the edge of that star there. Contact, they're right here. And then if they have that common envelope that they're so close, they're actually just sharing matter over there. So these are the two interesting systems, the semi-detached and the contact. Contact literally means the star surfaces are touching. They're touching as they orbit. It's kind of interesting. Okay, so here's another artist's conception of the red dwarf and matter flowing through this Lagrange point. And since everything's going around, the matter's going to wind around as it falls in. Because remember, when it gets past this point, it's attracted more to the white dwarf. It will tend to fall, and it goes around, creates a disk. We call that an accretion disk. And the disk can get hot. Why would it get hot? Friction, very good. There's friction between the particles, whatever it is, the gases. Usually hydrogen will be the major component, but there can be other things in there. So that will cause the disk to start glowing. And in fact, the disk becomes brighter than the white dwarf, the red dwarf combined. So you start to see this disk. Why is it brighter? Because it's so much bigger. And it's pretty hot. It's not as hot as a white dwarf, but it can be up to, maybe a few thousand Kelvin in there. So this is a computer simulation. We'll see more of these. This is a 3D model of that mass transfer that's going on. So here it is happening. This is a supercomputer simulation where you're going to see, you're not really seeing the mass come in. There it goes. And it's going to start to form a disk around the white dwarf, which is down here. And therefore, it's, again, feeding, giving mass to that. So that's going to cause changes on that white dwarf star as that happens. Okay. few things we do know. We can figure out the size of the disk if we know the masses of the two stars. And guess what we don't know? The masses of the two stars, at least the masters. In fact, most of my talk is going to be trying to get this quantity because this quantity appears in almost every relation. And you can't just go up to the stars and put them on a scale. You have to have some other way of figuring out that mass. And there's controversy on how to do that. So this would be the size of the disk. This is the brightness of the disk. M dot is the mass being transferred. We actually can measure that. And then this would be the temperature of the disk at some distance r into it. So we can figure out these quantities fairly straightforward once we know something about the masses of the stars involved. So, a few other things. Does anybody know about the asteroid belt? Anything about the asteroid belt? Is it like solid asteroids? No. They're in different orbits, right? Are there any gaps in it? Yeah, there's gaps. They're called Kirkwood gaps. Does anybody know what causes the gaps? My computational physics students hate me right now because we've been working on that there, and they had to write simulations with gravity producing it. It's the fact that if you take 2-1 gap, that's one of the big ones, for every one orbit of Jupiter around the sun, asteroids in that belt would go around twice. Okay, so let me see if I can do this. Okay? And that means it keeps getting tugged and tugged by Jupiter. It gets tugged here, and then it gets tugged again over here, and again over there. So it keeps getting these tugs. Those tugs pull it out of that particular position. We call that a resonance, that it keeps tugging on it and will pull it out so there's nothing there. Similarly, in this disk, the idea is that there's resonances. There's a 3-1 resonance. So the disk material going around 3 times for every one orbit of the white dwarf or the other star of the same period can lead to this pulling on the material, causing more friction as layers rub against each other. And that's going to cause a star to get brighter. Okay, has anybody here ever been to Russia? Okay. Do you know who Gorbachev was? Yeah? Okay. About 8 years ago, he came to our university, and I was his greeter and host, and got to chat with him. So he's kind of my buddy. And, it was kind of interesting. And he talked to the whole student body, and I had to introduce him. So I introduced him in Russian and English and did back and forth. And when he got up, he said he was confused because he thought everybody at our university understood Russian at first. But he's actually a very, very nice man. Actually, he did a lot to help end communism. So here is Moscow. This is Moscow State University. Overlooks the city. It's a Stalinesque building, this kind of structure. There's like 7 of them in Moscow. They're not particularly attractive, but that was that style at that time. I spent a sabbatical on a Fulbright grant teaching computational physics there one semester. And so I got to know more about the university and other people, and I eventually got this colleague at the Sternberg Institute, which is, maybe about a half a mile from that building. And we've been working now together for 10 years on various things. This is the Kremlin down in Moscow, and I think I might have some other shots coming up. Okay, my colleague Irina, that you can see over here, and these are 2 students I took over to Russia 6 years ago, and they did our research, gather all the data, because we don't stay up all night. We let them stay up all night. Much easier. So that was in our place where we stayed. We had a little dining area, so we would have dinner there. And this is one of the observatories we get to use. This is in Crimea. Do you know anything that happened to Crimea 2 years ago? Yes. Yeah, it kind of got taken over by Putin. And so we were supposed to go there in 2014. We didn't go. We are planning on going this coming summer again because things have calmed down in that area. So the Sternberg Institute has this Crimean observatory, and they have 11 telescopes there, which are really quite nice. This is the largest. It's a 2.6 meter, huge, 2.6 meter mirror on it. We don't use that one. That's for studying galaxies, but they showed it to us. And this is the building for it, and the 4 of us outside of it posing. This is one of the ones we use. We'll see inside in a minute. It's almost a meter, 9/10 of a meter. So that's a pretty good size telescope, much bigger than we have at our university. We only have a 16-inch telescope. And also, it's the observatory is a bit in a mountainous area. It's maybe 5,000 feet. It's not really, really high. But it has pretty dark skies over there. So the 0.9 meter is the one we're going to be using. And here is here's a view of it inside. What's really amazing to me is that the telescopes weren't computerized. I don't know about anybody here, but I can't find things very easily anymore. I mean, it's because I'm spoiled by a computer. Just punch in the name and the telescope moves to it, and it's usually pretty close. They still they use something called right ascension circles and things, and they calculate them, and they have a technician that moves it and tries to find it. And then it stays pretty much on target, although they keep checking it. But it wasn't computerized. That was a big surprise to me. This is actually the 0.6 telescope, 0.6 meter telescope, and we'll see some more. Unfortunately, you can't see all of it, but this is one of our field of views. This is what we're looking at in the center. And what was really exciting that summer was when we looked on a map, a chart of the sky, there was nothing there. And 2 days earlier, that star had suddenly appeared. Not visibly, with your naked eye, but had been picked up by some satellites. And so we decided, let's start taking data on this, because it was something brand new. No one had looked at it before. So what we do is we take our star, actually, let's get the one over there. This is our variable star. This is our comparison star, and that's our check star. So what you do is called differential photometry. You take images with a CCD camera, like that. Here's a negative of it. And then you pick stars that are going to be comparable or are in some catalog as being standard stars. And then you measure off of each photograph the number of photons that hit it, the number of pixels that have been excited by the light there. The central one goes around the star, and then there's a little annulus around there to measure the background light. And then you can subtract and figure out the magnitude or the brightness of your star. And if it changes, you're going to get the changes from that. So my students were taking the data and then doing this differential photometry. And here's that star over time. And you can see this is brightness in a red filter, and this is days, parts of days going on. This is the 386, 388, 389 code for days. And so you can see a brightness, not so bright, got bright. And over here, wow, it really started oscillating over there. And we'd like to know what's going on. The other thing is that it's getting less bright as it starts coming down here. So we had caught it. It probably would have started off really, really dim. It brightened and then came down gradually and then faded again. And so we caught it kind of at the peak as it started coming down. So here's a little close-up of some of the nights of data. As you can see, there's not a whole lot of data points, but there are enough for us to start to measure things from them and try to figure out quantities that can get us towards that mass ratio. So here's, again, a strip of all the days. And by the time we looked at the 18, we can see very much variation anymore. Okay. So, idea is to take images with a CCD camera and measure the brightness of the star over time. So what do we do with it? Well, the first thing we want to do is measure some periodicity. If it's brightening and dimming within that, because remember it's really bright, but there's still those little fluctuations as it dims, we want to say, okay, can we measure any periodicity? Can we find an orbital period of the stars in the data as well? Because that would be something we really need to know. So if you're in engineering, you probably will do, if you haven't already, signal processing. You have to know how to work with digital signals and different filters and stuff. And one of the things there is a discrete Fourier transform that you would learn. That's what we use. However, the one is a discrete Fourier transform. DC is data compensated because we have a problem you wouldn't have if you're measuring something in a lab. And that is we only get data at night and then have a big gap. And then maybe the next night, and we have a gap. So we have lots of gaps in our data. Do you ever have gaps in your data in lab? And then how do you handle it, especially if you're trying to look for some kind of sine or cosine signal? So there are ways to modify this, several ways. The other is Lom-Scargill. And so we try to apply those to our data to search for something. So here's the idea here. This is giving us what's basically the power, how much energy, if you want to look, is given to different frequencies. And this is going to be a phase diagram, important tool. If you have a signal that's varying, okay, and it keeps going over time, well, if you find the period, you look at it, and then at the end of that period, you take your next data and you fold it over to the beginning of that period. So you keep folding it over on the period. So your time is only from beginning to one end of a period. So we can go from 0 to 360 in phase. And so we keep piling up the data like that, and we get a phase diagram. So it's a way of increasing your signal, in a sense, by folding it over. Does everyone kind of understand that idea? It's a really powerful way of starting to look at them. So when you finally see something where there's like a peak out of all that data, then that tells you, yeah, there's probably a good period there. As you can see here, there's a couple of peaks. One down here and one down here. The one down here is the first one we're interested in, peak over here. There's all these other ones. Anybody have an idea why they're these? And I'll tell you, they're separated by 1 cycle per day. Yes.
Bell curves?
Actually, it's following a bell curve. Yeah, they'll follow bell curves because they'll get smaller and smaller. But why are they separated by 1 day? 1 day. Because we go out one night, and then we go out the next night, and the next night. We have a period of 1 day built in the way we take our data. So we would have, they're called aliases in the signal. Give you another interesting example of aliases. We got some data from Kepler on one of these stars, and I was analyzing it. And there's all these frequencies, and you have to pick out the ones that are real. Turns out that every 4.08 times a day, they have to fire a thruster on the satellite to keep it aligned because the gyros had broken. So they fire this every 4.08 times a day. So there was a big signal at 4.08 days. My colleague in Florida kept thinking, oh, this is great. We're gonna, no, that's artificial. Okay. And then there's another thing called the Nyquist frequency. You can't look at every frequency. You can only go so big in your data. So you have to be aware of that. And then there was another one I found by researching Kepler, that there was another one at 17 cycles per day that they use. It has something to do with the motor turning. So anytime there's any cyclic thing in your data, you will pick it up by this periodogram, by that Lom-Scargill. That's what this is, kind of signal. And then once you have this one, we have to try to understand what's that other signal due to over there. So here is the phase diagram. We're getting nice peaks. This is going to be for the, what we call super humps, the brightness of the star kind of going up periodically, and we can measure frequency for it. And there it is in this one. I removed the other signal, and just the 1 day ones are there, and we can measure it. And it's 0.096043 days. You can measure these things really, really precisely as you do this. So, oops, sorry. Let's go back here for 1 second. And then an important quantity is called the superhump excess. How does the superhump period differ from the orbital period? And I don't have the graph in here, but we also were able to pick out the orbital period. The orbital period and this period differed by 0.054. And why the two periods? Okay, here's the idea. One is from the disk. We have this disk. The disk, as you're going to see, is elongated, and it's moving around as the stars move around. So we have the orbital period, and then we get this disk. This disk is what we call precessing. You know how a top, you spin a top and put it, starts moving around like this, as you know, it's spinning, but it moves around. That's precession. This disk does the same thing. And so this is measuring that precessional period, and then we have the orbital period. And researchers have defined this quantity as something to look at to try to tie to that mass ratio. Okay, so if we look, by the way, most stars have a positive number for epsilon, which means the disk is kind of leading in the orbit as it goes around. See all the dots there, and all the blue ones are dwarf novae that we're looking at. And then there's a few that are lagging. They're negative ones over here. We haven't found any negative ones. We found only positive superhumps there. Okay, another thing. If you compare the predicted maximas on your curve and compare it to the observed, this is observed minus calculated or predicted, we measure that, and then this is just days or number of orbits as we go on. It fits a parabola. That tells us that the period is changing very, very slightly, but it's changing, and we can measure that change here on Earth. By the way, this star is about 1,000 light years away. So it's amazing you can figure out these things from these signals. So this is tied to that mass transfer ratio, that as the period changes due to conservation of angular momentum, as mass is changing, there has to be a change in the period, and we're able to pick that up. Okay, finally we're going to go into modeling of this. That's kind of the data end. So I do the data analysis. My students and Irina take the data, and then Michelle actually does the simulations. So we use a couple of things. Kepler's law, period squared, the orbital period squared is proportional to the cube of the semi-major axis A. That's the distance between the red dwarf and the white dwarf. And then there's another, this is a semi-empirical relation from theory that should give us the size of the secondary star there. So a few more relations. We don't need to know those. But here's going to be the thing. So now we do some modeling. I'm going to show you some animations, actually the data of this, a movie of it. But we start to get a disk. You're not seeing the stars in this one. Like, can everyone see like this in here and the upper one coming in? We find out as matters transfer, there's kind of waves of matter getting scrunched. And those waves of being scrunched is really helping to lead to the brightness of things. More friction will occur there as things get pushed together. Let's see. Okay, there we go. Let's go back. Okay, so here is that wave that I mentioned over here. Here's the red dwarf star. Here's the matter flowing in over there. And there are these waves as it's going around. And if there's that resonance, if the disk gets to grow to the size of the resonance, that's disturbing this, and it's causing probably things to move together, apart from one region, together in another, and we get these kind of waves that travel in there. Okay, so what we do is, let me go because let me just show you the movie here. How can I get to a mouse on here? I need to, oh, there it is. Okay, that might help if I turn the mouse around. Here we go. So, here is the simulation, kind of quick. So you're going to have to watch it very quickly as it's forming and we get those waves that I've been talking about going on. Okay. So now let's go back here. So here is the brightness, this is the time, and so the star got brighter, a little dimmer, then got kind of brighter again. But when you look inside, you see all these squiggles. Those are the squiggles we measure, and this is the model predicting these squiggles, and then this tells us what is the frequency of those squiggles, and we are able to get it within 1% of our measured value. So, why do we do the model? Because the model is going to tell us the mass ratio. And that's what we're looking for. That's the only way we think we can get the mass ratio. Other people have some other ideas, but we think this, by looking in, and here we're zoomed in on, and here's close of a few frames from around day or orbital period 100, we're getting the mass ratio for these systems. Okay, I'll skip that one. So, the end result from our work is that we're trying a different way of determining the two masses of the stars, or the mass ratio. And then usually we can pretty much know something about masses of white dwarfs, and we can figure out the mass of the other star that way. So the bottom line is that we're looking at a star that somehow has filled its Roche lobe, it's transferring mass to the white dwarf. As the mass flows in, at times it maybe builds up enough and it starts a dwarf nova, the star becomes a lot brighter, and that disk is moving around. Okay, how's this related to a nova and a supernova? Well, do you think this matter in the disk just stays there? Because there's friction on it. What happens when you have friction? Heats up and it loses energy, right? And if they lose energy, they're going to start to fall closer in. So that mass eventually settles on the white dwarf. Okay. And if some of it builds up and gets dense enough, and fusion of the hydrogen, because it's hydrogen mostly from there, can take place, we suddenly have fusion reactions going on in the atmosphere of this white dwarf, and that's a nova. So, you know, nova are definitely related to us. And so here we're kind of seeing a nova again, with all this light getting out, as some fusion reactions are created on there. But there's something else. Does anybody know what the maximum mass of a white dwarf is? It's a magic number. 1.4 times the mass of our sun. You can't have white dwarf stars more massive than that. Gravity would then crush it. Does anybody know what prevents a white dwarf star from collapsing? It's called electron degeneracy. Degeneracy. And let me just give you a quick idea. If we were to play musical chairs in here, and I started playing, you know, you all did that as a kid. So if I started playing some music and you had to run around and come back and grab a chair, and we kept removing a chair, you just kicked out, right? Well, in white dwarfs, when the matter gets so dense, there's not a room anymore for electrons to be in a grid, if you want to look at it, have a place in this grid. So they're kind of repelling each other, not by their charge, but just by quantum mechanics, to be in the same place at the same time, called the exclusion principle at work. But it gets onto a big scale there. So that preventing electrons from going inwards anymore is what supports the white dwarf star. That would be the electron degeneracy. And the maximum mass that could support is 1.4 times the mass of the sun. So we know this is a very well-established number. It's known as the Chandrasekhar limit there. So what happens if some of that mass settles on and it doesn't have fusion and it keeps accumulating and accumulating? What's going to happen? Something has to happen. If it gets beyond 1.4 solar masses, something has to happen. Any idea? Any idea? Not a black hole. It's going to be that when all of that forms, the white dwarf is mostly carbon. Carbon. You've all of a sudden got extra mass, and the whole star explodes in a fusion called carbon detonation. And that's our type 1a supernova. Explosion of a star in this binary system. Now you're probably wondering, what happens to the other star? Probably gets pretty much destroyed. Pretty close, and it's pretty powerful. So here's a look again at matter coming in. So this is the star that's going to explode. The white dwarf as a lot of matter accumulates on it. Okay. And remember, in all those equations, it was the ratio of the masses that also determines how much matter is flowing in. So that's why we want to know that quantity so badly. So here's a couple type 1a supernovas. And there's a satellite, no, it's not a satellite, it's Earth-based telescopes called the SASN, which is All Sky Surveys, All Sky Supernova Search something. All Sky Search for Supernovae, SASN, and it looks for them. So here's the remnant of one. This is a very, very old one. And of course, when that star explodes, things go off into space. What kind of things go off into space? Well, carbon, okay, and something else we think that these stars can produce during that, and that is going to be iron. Let me go to the other slide. I got too many words there. Iron. So here is, this might be SCA1. And so we think there's a lot of iron that is sent out by these particular type 1a supernovae. And we also think that they're almost like bullets being shot out into space. So what would happen if the nearest star to the sun were to become a supernova? Yeah, we get hit by iron bullets, we get hit by gamma rays, get a lot. Yeah. So that would be the production. So here's another X-ray image looking out of it. So the idea now that we see is those little stars that are the size of the Earth can have the most powerful explosions that we observe out in space. And it's all due to this mass transfer in this binary. They're all in binaries in order for this to have, and we're trying to understand that process that goes on over there in time. So I'm going to kind of wrap up now, and here we are again outside of Moscow State University, and what they can say was this. So thank you. If you have any questions, I know this is kind of really compact way of looking at it. If you have any questions, maybe we could take some. No.
Well, I'm sure he'll be around for a few minutes, and also we'll be at the choice room for lunch. If you want to come and talk about Russia, or Putin, or Trump, or anybody else. All right. And let's thank our speaker again.